3 coronal mass ejections, each one a billion-ton blast of solar plasma, ripped from the far side of the sun, aimed straight toward one tiny interstellar intruder, 3I Atlas. And then, silence. It didn't slow, it didn't swerve, it didn't even flinch. But the sun did. Solar activity spiked, magnetic fields twisted, and yet the object's orbit, perfect, unshaken. How can something from another star system shrug off the full fury of our sun? Stay with me until the end, because the data we present suggests something unthinkable. 3I Atlas may not just be passing through our system, it may be testing it. If this mystery has you on edge the way it has me, make sure to hit like and subscribe because you don't want to miss a single update as this unfolds in real time. Tell me where you're watching from, what time it is there, and what you think about this interstellar visitor. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The impossible stability. Something is moving through the inner solar system right now that shouldn't exist. I don't mean it shouldn't be here, travelling through our cosmic neighbourhood on a trajectory from somewhere unimaginably distant. We've seen interstellar visitors before. I mean, it shouldn't be possible for it to behave the way it's behaving. Because according to every model we have, every equation we trust, every principle of orbital mechanics and plasma physics that governs how objects move through space, 3I Atlas should have been deflected. It should have been pushed, even slightly, off its predicted course when the sun threw everything it had at this thing, but it wasn't. Let me back up for just a moment so you understand exactly what we're dealing with here. On July 1st, 2025, the Atlas telescope in Chile picked up a faint smudge moving against the background stars. Nothing unusual about that. Telescopes find objects all the time. But within hours, astronomers realised this wasn't just another comet or asteroid making its routine lap around our star. The orbit was wrong. Wildly wrong. The trajectory wasn't an ellipse bringing it back someday. It was a hyperbola, an escape curve, the mathematical signature of something that came from outside and is just passing through. This was the third confirmed interstellar object ever detected, and they gave it a designation that sounds more like a cipher than a name: 3I Atlas. Now here's where things get interesting in that special way that makes astronomers lose sleep. When they calculated its orbit with increasing precision over the following weeks, they found an eccentricity of around 6.1, maybe 6.2. For reference, anything above 1.0 means the object isn't bound to our sun, but 6? That's absurdly hyperbolic. This thing is moving at roughly 60 kilometers per second relative to the sun's rest frame, which means when it finally leaves our solar system, it'll still be travelling at that breakneck speed, into the darkness between stars. It came from somewhere out there in the galactic thick disk, potentially billions of years old, potentially older than our entire solar system, and it's just cutting through on a one-time visit. The European Space Agency and various observatories tracked it meticulously. They calculated that it would reach perihelion, its closest approach to the Sun, in late October 2025, just inside the orbit of Mars at about 1.35 astronomical units. That's roughly 200 million kilometers from the Sun, close enough to heat up significantly, far enough to avoid vaporizing. The Hubble Space Telescope got a good look at it on July 21st, 2025. The images showed a classic cometary structure, a nucleus surrounded by a glowing coma, a tail being blown back by solar radiation and the solar wind. Spectroscopy from the James Webb Space Telescope revealed something unexpected, though. The gas coming off this thing is unusually rich in carbon dioxide, not the water and carbon monoxide mix we see in most comets. Carbon dioxide, that tells us something about its chemical composition, its thermal history, maybe even the conditions in whatever stellar nursery spawned it billions of years ago. Then 3I Atlas did something that made tracking it extremely difficult. It passed close to Mars on October 3rd, close enough that spacecraft orbiting the red planet like the ExoMars Trace Gas Orbiter captured imagery confirming its position. Right where the prediction said it would be. No deviations, no surprises. But after that Mars encounter, from Earth's perspective, the object moved behind the Sun. Superior conjunction, astronomers call it. When something passes on the far side of the Sun relative to Earth, You can't see it through regular telescopes anymore because the sun's glare drowns out everything. The object effectively vanishes behind a wall of light. This is where coronagraphs become essential. These are specialized instruments designed to block out the sun's disk, so you can observe the area immediately around it, the corona, the solar wind, and anything else moving through that region. Satellites like GOES-19 carry coronagraphs, so do spacecraft at specific orbital positions, and this is where independent observers, amateurs and professionals alike, started reporting something extraordinary. They claimed they could see 3i Atlas, faint but detectable, moving through the coronagraph frames exactly where the predicted ephemeris said it should be. Frame by frame, this tiny smudge of reflected light crept along its calculated path through one of the most hostile environments in the solar system, the immediate vicinity of our actively erupting star. And that's when the sun decided to make things interesting. According to reports emerging from people analysing coronagraph data and solar weather logs, 3 massive coronal mass ejections launched in rapid succession from the far side of the sun. Not from regions facing Earth, which is why most people didn't hear about them, but from the far side, from active regions rotating away from our view. And here's the critical detail. The timing and trajectory of these CMEs aligned with the predicted position of 3i Atlas. Picture a plasma cannon firing 3 times in quick succession, each burst containing billions of tons of magnetized solar material travelling at hundreds or thousands of kilometres per second, all converging on a tiny interstellar interloper barely a few kilometres across. A coronal mass ejection isn't just a puff of hot gas. It's a wall of ionized particles, magnetic field lines twisted into chaotic knots, electromagnetic forces on scales that dwarf anything we can produce on Earth. When a CME hits a comet, it can strip away parts of the coma, compress the tail, create shock waves in the surrounding plasma. And if the momentum transfer is significant enough, if enough of that kinetic energy couples into the nucleus itself, it should alter the orbit, even slightly. Even by an amount that would only show up as a tiny deviation from the predicted path over days or weeks, but it should happen, except it didn't. The object that emerged from behind the sun in the coronagraph imagery, the faint smudge that continued along its trajectory after those 3 CMEs supposedly slammed into it or past it, was exactly where the original ephemeris predicted it would be. No deflection, no deviation. No measurable change in velocity or direction. As if those CMEs, those gargantuan eruptions of solar fury, had simply passed through it, or around it, without imparting any momentum at all. Which brings us to a hypothesis that sounds like science fiction, but is being discussed in certain circles with increasing seriousness. What if 3i Atlas isn't just passively drifting through the sun's magnetic field? What if it's interacting with it? What if this object, with its dusty coma and plasma envelope, is somehow short-circuiting the sun itself, creating a feedback loop where its presence triggers electromagnetic disturbances in the solar atmosphere, and those disturbances manifest as CMEs directed back at the very object causing them? And what if that same electromagnetic coupling acts as a kind of shield or stabilizer, preventing the CMEs from deflecting it the way simple Newtonian mechanics would predict? I know how that sounds. But stay with me, because if there's even a kernel of truth to this idea, we're not just looking at a weird comet. We're looking at something that could force us to rewrite our understanding of how interstellar objects interact with stars, how plasma physics operates on scales we've never observed before, and maybe, just maybe, what kinds of structures or compositions could exist in objects wandering between the stars. Because whatever 3i Atlas is, it's not behaving like anything we've seen before, and that means everything we thought we knew about objects like this might be incomplete. So let's unpack this mystery piece by piece, test the theories, examine the evidence, and explore some wild but just barely plausible scenarios. Because something hit 3i Atlas with the force of a solar storm, and it didn't budge, and we need to figure out why. Part 2. Tracking the interloper. We need to establish exactly what we know about 3i Atlas before we dive into the truly strange parts of this story. Because the foundation here, the observational record, is actually quite solid, even if the interpretation is about to get weird. When the Atlas Survey Telescope in Chile first spotted this object on July 1st, 2025, it appeared as nothing more than a faint dot moving slowly against the fixed stars. But within 24 hours, as other telescopes around the world picked it up and added their measurements, The orbit calculators started spitting out numbers that made people sit up and take notice. The eccentricity came back around 6.1 to 6.2. In orbital mechanics, eccentricity is a measure of how elliptical or circular an orbit is. 0 means perfect circle. Values between 0 and 1 describe ellipses, the classic closed orbits we associate with planets and most comets. Exactly 1 is a parabola, the boundary case. Anything above 1 is a hyperbola, an open curve that never closes, never comes back. An eccentricity of 6 means this object is moving so fast that the sun's gravity well barely even curves its path. It came from interstellar space travelling at about 60 kilometers per second, and when it leaves it'll still be moving at roughly that speed. The sun just gives it a gravitational assist, bending its trajectory slightly, but ultimately it's just passing through our neighbourhood on its way to somewhere else in the galaxy. The Virtual Telescope project and other observatories quickly refined the trajectory. Perihelion, the closest approach to the Sun, was calculated for late October 2025 at a distance of approximately 1.35 astronomical units. 1 AU is Earth's average distance from the Sun, about 150 million kilometres, so 1.35 AU puts perihelion just inside Mars' orbit, close enough to experience significant solar heating, but not so close that the nucleus would sublimate catastrophically like some sun-grazing comets do. This was going to be a relatively mild perihelion passage by solar standards, which made it all the more surprising when things got dramatic later on. NASA's Science Assets Division coordinated observations across multiple platforms. The really crucial data came on July 21st, 2025, when the Hubble Space Telescope turned its instruments toward 3I Atlas and captured high-resolution imagery. What Hubble saw was a classic cometary structure, a central nucleus surrounded by a diffuse coma of gas and dust being liberated by solar heating, and a tail streaming away from the sun shaped by radiation pressure and the solar wind. Hubble's measurements allowed astronomers to constrain the size of the nucleus itself. Based on brightness and albedo assumptions, they estimated the nucleus was probably no larger than about 2.8 kilometers in diameter. That's small by cometry standards, roughly comparable to the nucleus of Halley's Comet, but still massive enough to produce the coma and tail structure they were observing. Then came the James Webb Space Telescope's contribution. JWST can do spectroscopy that Hubble can't match, breaking down the light from the coma into its constituent wavelengths, and identifying specific molecules based on their absorption or emission lines. What JWST found was unusual. The coma was dominated by carbon dioxide, not water vapour, which is the primary volatile in most comets from our solar system, not carbon monoxide, another common cometary gas, carbon dioxide, CO2. That tells us something profound about this object's composition and thermal history. Carbon dioxide sublimates at higher temperatures than water ice under most conditions, and its dominance suggests either that 3I Atlas formed in a region of its birth system that was relatively warm, or that it has lost most of its more volatile components during billions of years of exposure to cosmic rays and occasional stellar encounters. Either way, it's compositionally distinct from the typical comets we see in our own Oort cloud or Kuiper belt. Now we get to October 3rd, 2025. 3I Atlas made a close approach to Mars, passing within a few million kilometers of the red planet. This was a stroke of observational luck because multiple spacecraft orbiting Mars, including the ExoMars Trace Gas Orbiter, operated by the European Space Agency and Roscosmos, were positioned to observe the object as it flew past. They captured images confirming its position and velocity. The data showed no deviation from the predicted trajectory. This is important because it establishes a baseline. As of early October, before the object moved behind the Sun from Earth's perspective, its orbit was exactly where the calculations said it should be. No surprises, no unexplained accelerations or decelerations, just simple Keplerian mechanics with a bit of non-gravitational force from outgassing, the kind of thing we expect from active comets. Then came the conjunction. As 3I Atlas continued inward toward perihelion, its position in the sky moved closer and closer to the Sun as seen from Earth. By mid-October, it had effectively disappeared into the solar glare. Normal optical telescopes were useless at this point. The Sun is so overwhelmingly bright that trying to see a comet near it through a regular telescope is like trying to spot a firefly hovering next to a searchlight. You need specialized equipment designed specifically to block out the sun's disk and observe only the surrounding region. This is where coronagraphs become essential tools. A coronagraph is an instrument that uses an occulting disk or other method to physically block the light from the sun's photosphere, revealing the much fainter corona and the space immediately around the sun. Satellites like GOES-19, positioned in geostationary orbit, carry coronagraphs for monitoring solar wind and CME activity. The Solar and Heliospheric Observatory, SOHO, has been doing this for decades from its position at the L1 Lagrange point. The stereo spacecraft, positioned at different angles around the sun, provide additional perspectives. All of these instruments can, in principle, detect objects moving through the inner heliosphere, including comets passing near the sun. And this is where independent observers started reporting detections. People analysing publicly available coronagraph imagery claimed they could see a faint object moving through the frames in late October 2025, right around the time 3I Atlas was supposed to be near perihelion behind the sun. The object's motion matched the predicted ephemeris. Its brightness was consistent with a small nucleus reflecting sunlight at that distance. Frame by frame, day by day, the little smudge crept along exactly the path that had been calculated months earlier, based on observations taken before the conjunction. No deviation, no surprise accelerations, just the smooth, predictable arc of an object following Newton's laws and Kepler's equations. But here's where the story takes its first sharp turn into the strange. During that same period, while 3I Atlas was behind the sun from our perspective, solar observatories recorded something unusual. 3 large coronal mass ejections erupted in quick succession from active regions on the far side of the sun. The far side, meaning the hemisphere facing away from Earth, the side we can't directly observe from our planet, but can sometimes monitor using spacecraft positioned off to the sides, or by analysing heliosysmology data. These weren't Earth-directed CMEs, which is why they didn't make the news and didn't trigger geomagnetic storm warnings. But according to reports now emerging, the timing and geometry of these eruptions aligned disturbingly well with the predicted position of 3I Atlas. Think about the geometry for a moment. Earth is on one side of the sun. 3I Atlas is passing near perihelion on the opposite side, behind the sun from our perspective. An active region on the far side of the sun erupts, launching a CME outward in the general direction where 3I Atlas happens to be at that moment. Then it happens again, and again. 3 times. 3 massive bursts of magnetized plasma, each one containing perhaps billions of tons of material, travelling at speeds that could range from a few hundred to well over 1,000 kilometers per second, depending on how energetic the eruption was. And all 3 aimed, whether by coincidence or something stranger, in the direction of a tiny interstellar visitor. So the question becomes, did those CMEs hit 3I Atlas, or pass near it, or interact with its coma and plasma environment in some way? And if they did, why didn't we see any deviation in the orbit? Because that's the real mystery. The coronagraph observations that came after the conjunction show the object exactly where it was supposed to be. No deflection. Which means either the CMEs missed it entirely, or something is very wrong with our understanding of how CME impacts should affect small bodies, and that's where this story stops being a simple tale of tracking an interstellar comet and starts becoming something much more troubling and fascinating. Part 3, When Solar Storms Strike. We need to talk about what a coronal mass ejection actually is, because the term gets thrown around a lot in space weather reports and documentaries, but most people don't really grasp the sheer scale and violence of these events. A CME is not a solar flare, though the two often occur together. A solar flare is a sudden brightening, an intense burst of electromagnetic radiation across the spectrum from radio waves to X-rays, caused by magnetic reconnection in the sun's atmosphere. It travels at the speed of light and reaches Earth in about 8 minutes. A CME is different. A CME is a physical eruption of plasma, a chunk of the sun's corona being violently expelled into space, carrying with it tangled magnetic field lines embedded in that plasma. When a CME launches, billions of tons of ionized hydrogen and helium, along with traces of heavier elements, blast outward from the sun at velocities that can range from a few hundred kilometers per second for weak events to over 3,000 kilometers per second for the most extreme eruptions. The material forms an expanding cloud, sometimes visualized in coronagraph images as a bright halo or loop structure racing away from the sun. This isn't just hot gas, it's magnetized plasma, which means it carries frozen-in magnetic fields that can interact with other magnetic structures in space. When a CME hits Earth's magnetosphere, those interactions cause geomagnetic storms, auroras, and occasionally disruptions to satellites and power grids. Now imagine what happens when a CME encounters a small body like a comet. The comet has no global magnetic field like Earth does, no protective magnetosphere to deflect the incoming plasma. It's just a solid nucleus, maybe a few kilometers across, surrounded by a diffuse coma of gas and dust being liberated by solar heating, and trailing behind it a plasma tail shaped by the solar wind. When the CME arrives, the first thing that happens is a shock wave. The leading edge of the CME compresses the ambient solar wind and any cometary plasma in its path. This creates a pressure wave that can compress the coma, brighten the plasma tail, and potentially strip away outer layers of gas and dust. But here's the critical question. Can a CME deflect a comet's orbit? Basic physics says yes, it should be possible. The momentum carried by billions of tons of plasma moving at hundreds or thousands of kilometers per second is substantial. If even a fraction of that momentum transfers to the solid nucleus of the comet, you'd expect some change in velocity. It might be small, maybe only a few meters per second or less depending on the geometry and the comet's mass, but it should be measurable over time as the comet's position drifts away from the predicted ephemeris. Let's put some rough numbers to this. Assume a typical large CME contains about 10 to the 16th grams of material. That's 10 billion grams or 10 trillion kilograms, travelling at let's say 1,000 kilometers per second. The momentum is mass times velocity, so that's 10 to the 19 gram centimeters per second, or 10 to the 16th kilogram meters per second. Now assume 3I Atlas has a nucleus with a radius of about 1.4 kilometers, based on that 2.8 kilometer diameter estimate from Hubble. If it's made of typical cometary material with a density around half a gram per cubic centimetre, that gives a mass of roughly 6 times 10 to the 15th grams, or 6 trillion kilograms. If the CME hits it head-on, and even 1% of the CME's momentum transfers to the nucleus, that's still a momentum change of about 10 to the 14th kilogram meters per second. Divide by the comet's mass, and you get a velocity change on the order of maybe 20 meters per second. 20 meters per second doesn't sound like much, but over days and weeks, that compounds. The comet's position would shift noticeably from its predicted path. Observers tracking it would see it arrive at perihelion slightly early or late, or shifted in its orbital plane, depending on the direction of the impact. Astrometric measurements should be able to detect deviations of that magnitude fairly easily, especially with modern telescopes and spacecraft tracking systems. So if 3 CMEs hit 3I Atlas, each potentially transferring momentum, we should see evidence of deflection. The orbit should change, the ephemeris should need updating. But according to those coronagraph observations, it didn't happen. The object stayed on course. Which brings us to 3 possibilities. First, maybe the CMEs missed it entirely, passing nearby but not actually intersecting the nucleus or even the inner coma. Space is big, and aiming a CME is not like aiming a rifle. The CME is more like an expanding shell of material, and if 3I Atlas was off to one side of the main concentration of plasma, maybe it just didn't get hit hard enough to matter. Second possibility, maybe our estimates are wrong. Maybe the nucleus is much more massive than we think, dense enough that the momentum transfer from the CMEs was negligible compared to the object's inertia. But that would require densities far higher than typical cometary material, more like rock or even metal. And while 3I Atlas is strange, there's no indication from its brightness or coma structure that it's a solid iron cannonball hurtling through space. Third possibility, and this is where things get genuinely weird, maybe something about 3I Atlas prevented the momentum transfer. Maybe its coma has properties that shield the nucleus, or maybe there's an electromagnetic interaction happening that we don't fully understand, something that couples the CME's energy into the plasma environment around the object without translating into a net push on the solid nucleus itself. This is the short-circuiting hypothesis, and we're going to examine it in detail because it's simultaneously the most speculative and the most intriguing explanation on the table. But first, let's nail down the timeline and the evidence. The CMEs in question allegedly erupted in late October 2025, around the time 3I Atlas was near perihelion. Solar weather archives should contain records of these events. CMEs are routinely catalogued by observatories like SOHO and Stereo, with details about timing, speed, direction, and estimated mass. The problem is that far-side CMEs are harder to characterize because we don't have direct coronal imaging of the far side of the Sun from Earth's vicinity. We rely on helioseismology, which uses sound waves travelling through the Sun to infer activity on the hidden hemisphere, and on data from spacecraft positioned off to the sides like Stereo. So the evidence for these specific CMEs may be indirect or incomplete. What we do know is that active region numbers and sunspot groups rotate with the Sun, completing one rotation every roughly 27 days as seen from Earth. An active region on the far side today will rotate into view in about 2 weeks. If there was unusual activity on the far side in late October aimed at 3i Atlas, those same active regions should have rotated into Earth-facing view in mid-November. Did they produce more eruptions? Did they show signs of being particularly large or energetic? That's the kind of detective work that could help confirm or refute the claim that these CMEs were real and significant. And then there's the geometry. For a CME to hit 3i Atlas while the object is behind the Sun from Earth's perspective, the eruption has to come from a source region that's also on the far side, roughly aligned with the object's position. CMEs expand as they propagate, so they don't have to be aimed with laser precision, but there does have to be geometric alignment. Someone with access to full solar weather data and orbital mechanics software could simulate this, tracking where 3i Atlas was at specific times, and where CMEs launched from specific source regions would have propagated. If the alignment is good, the claim becomes more plausible. If the alignment is poor, maybe this whole story is a case of correlation mistaken for causation. But here's what troubles me. The coronagraph detections showing 3i Atlas exactly on track after the alleged CME impacts are hard to dismiss. If those observations are accurate, and if CMEs did intersect the object's path, then we have a genuine puzzle. Either the object is far more massive than it appears, which raises questions about what it's made of, or something more exotic is going on. And that brings us to the hypothesis that sounds like it belongs in a science fiction novel, but is starting to gain traction in certain corners of the astronomy community. The idea that 3i Atlas is electromagnetically interacting with the Sun in a way we've never observed before. That it's somehow triggering the very CMEs being launched toward it and simultaneously shielding itself from their effects, a cosmic feedback loop, a short circuit between star and interloper. Part 4. The Short Circuit Hypothesis. Let me introduce you to an idea that's going to sound completely absurd at first, but bear with me because once you understand the physics involved, it becomes just barely plausible enough to be worth taking seriously. The hypothesis goes like this. 3i Atlas is not just passively moving through the Sun's magnetic field and solar wind like a piece of cosmic driftwood. Instead, it's actively interacting with the Sun's electromagnetic environment, creating disturbances in the local plasma, modifying current flows and magnetic field line topology in ways that feed back to the Sun itself. And those feedback effects, according to this hypothesis, can trigger the release of stored magnetic energy in the solar corona, manifesting as coronal mass ejections aimed back toward the very object causing the disturbance. It's a kind of electromagnetic coupling between object and star, a circuit where the object acts as a perturbation or anomaly in the current flow, and the Sun responds by short-circuiting, dumping energy in the direction of the disturbance. I know, it sounds crazy. But let's break down the physics piece by piece and see where this idea comes from. Start with what we know about how comets interact with the solar wind. A comet approaching the Sun sublimates volatiles from its nucleus, creating a coma of neutral gas that expands outward. That neutral gas gets ionized by ultraviolet light from the Sun and by interactions with the solar wind plasma. Once ionized, those atoms become charged particles, and charged particles respond to electromagnetic fields. The solar wind is not just a flow of neutral gas, it's a plasma, an ionized gas threaded with magnetic field lines. When the cometary ions interact with the solar wind, they get picked up by the magnetic field and carried downstream, forming the classic plasma tail or ion tail that always points away from the Sun regardless of the comet's direction of motion. This interaction creates a region around the comet called the cometopause, where the cometary ions and the solar wind ions meet and interact. There's a bow shock upstream where the solar wind first encounters the obstacle of the coma, and there's a complex zone of mixing and energy transfer, Spacecraft have flown through cometary plasma environments and measured these structures directly. We know they exist. We know they involve currents and magnetic fields and plasma instabilities. What we don't normally see is any evidence that these local interactions feed back to the Sun in a significant way. The comet is a tiny perturbation in a vast system. The Sun has so much energy and magnetic flux that a small comet's plasma environment shouldn't matter to solar activity. But what if 3I Atlas is different? What if its coma is unusually dense or conductive? What if it has properties that make it a particularly strong current carrier or magnetic field perturbation? One possibility that's been floated is that the object might contain conductive material in its nucleus or dust grains, perhaps metal or carbon compounds, that enhance the electrical conductivity of its coma. Another possibility is that the sheer amount of gas being liberated, combined with the unusual CO2-rich composition, creates a plasma environment with different properties than typical water-rich comets. Carbon dioxide ionizes differently than water, has different collision cross-sections, different charge-to-mass ratios. Maybe that matters. Then there's the question of scale. 3I Atlas is moving through the inner heliosphere at 60 kilometers per second relative to the Sun. That's fast, much faster than most comets we observe, which are bound to the solar system and have lower velocities at a given distance. High velocity means the interaction time is short, but it also means the object is cutting through magnetic field lines at high speed, potentially inducing larger electric fields through Faraday's law of induction. Moving a conductor through a magnetic field generates an electromotive force. If the coma has conductive properties, the object's motion through the Sun's magnetic field could generate voltage differences across the coma, driving currents that wouldn't exist for a slower-moving object. Now here's where we venture into more speculative territory. The Sun's corona is a magnetically dominated plasma environment, where the magnetic field energy density exceeds the thermal energy density. The corona is threaded with magnetic field lines anchored to the photosphere below, and these field lines can store enormous amounts of energy when they're twisted or sheared by motions in the convection zone beneath. Sometimes that stored energy is released suddenly through a process called magnetic reconnection, where oppositely directed field lines come together, annihilate each other, and convert magnetic energy into kinetic energy and heat. This is what powers solar flares and coronal mass ejections. The hypothesis, then, is that 3I Atlas moving through the corona or near-corona region could act as a trigger for magnetic reconnection. Maybe its plasma environment perturbs the local field structure just enough to bring oppositely directed field lines into proximity. Maybe currents flowing through its coma provide a conductive channel that facilitates reconnection. Maybe its presence creates a magnetic anomaly that destabilizes an already stressed coronal magnetic structure. If any of this happens, the result could be a CME launched from the region of disturbance, which would be in the direction of the object itself, since that's where the perturbation is located. And here's the kicker. If the CME is triggered by the object, and if the object has some kind of electromagnetic shielding or current balancing effect that redistributes the CME's momentum without imparting a net force on the nucleus, then you'd observe exactly what the coronagraph data shows. CMEs aimed at the object but no orbital deflection. The object triggers the gun pointed at itself, but the bullet passes through or around it without pushing it. This sounds like science fiction, I'll grant you that. But let me give you some context for why it's not completely outside the bounds of physics. There's a scientist named Hannes Alfvén who won the Nobel Prize in 1970 for his work on magnetohydrodynamics, the study of how plasmas and magnetic fields interact. Alfvén was one of the pioneers of plasma cosmology, and he argued that electromagnetic forces play a much larger role in astrophysical systems than mainstream astronomy typically acknowledges. He talked about electric currents in space, about magnetic field line circuits, about how plasma doesn't always behave like a neutral gas, but has collective behaviours driven by long-range electromagnetic interactions. Now, most of Alfvén's specific ideas about cosmology didn't gain traction, and he's sometimes cited by proponents of fringe theories like the electric universe hypothesis, which takes his ideas to extremes that most scientists don't accept. But the core insight that plasmas can exhibit non-local, electromagnetic-dominated behaviour is solid physics. And if you're willing to entertain the possibility that an interstellar object with unknown composition and unknown plasma environment might interact with the Sun's magnetic field in unusual ways, then you're operating in a regime where Alfvén's kind of thinking becomes relevant. We know comets have plasma tails. We know those tails involve currents and magnetic fields. We know spacecraft have measured complex electromagnetic structures around comets. What we don't know is whether any of that can feed back to the sun strongly enough to trigger CMEs. Mainstream solar physics would say no. The scales don't match, the energy budget doesn't work out. But what if the object is acting more like a catalyst than an energy source? What if it's not providing the energy for the CME, but just providing the trigger that releases energy already stored in the coronal magnetic field? In that case, you wouldn't need the object to be electromagnetically powerful. You just need it to be in the right place at the right time, with the right properties to tip a metastable system over the edge. And then there's the shielding question. How could an object avoid being deflected by a CME impact? One possibility is geometric. If the coma is large enough and diffuse enough, the CME's momentum might be absorbed by the coma without reaching the nucleus. The nucleus is only a few kilometers across, but the coma can extend for tens of thousands of kilometers. If the CME's force is spread out over that large volume, the net push on the nucleus might be very small. Another possibility is electromagnetic. If currents induced in the coma create their own magnetic fields, those fields could interact with the CME's magnetic structure in ways that redirect or balance the forces. Imagine the coma acting like a magnetic sail, where the interaction is not mechanical impact but magnetic pressure, and the geometry of the fields cancels out net momentum transfer. These are all speculations stacked on speculations. But here's why I'm spending time on this. If there's even a small chance this hypothesis has merit, it would revolutionize our understanding of how small bodies interact with stellar environments. It would mean that interstellar objects aren't just passive test particles tracing orbits, but active participants in the electromagnetic ecology of the systems they pass through. It would open up entirely new questions about what kinds of objects might exist out there in the galaxy, wandering between stars, carrying with them properties and compositions we've never imagined. And it would mean that 3I Atlas, this tiny visitor from the void, might be the key to unlocking a new branch of astrophysics we didn't even know was missing. Part 5. Why it didn't budge. Let's get quantitative for a moment because we need to understand just how surprising it is that 3I Atlas apparently didn't budge when those CMEs hit. To do that, we need to work through some basic orbital mechanics and figure out what kind of deflection we should expect under different scenarios. Then we can compare that to the observational constraints and see where the mystery really lies. Start with the object itself. Hubble observations suggest the nucleus is no larger than about 2.8 kilometers in diameter. Let's assume it's roughly spherical for simplicity and work out its mass under different density assumptions. If it's made of typical cometary material, low-density water ice and dust, with lots of porosity, the bulk density might be around 0.5 grams per cubic centimeter, similar to Comet 67P Churyumov-Gerasimenko, which was visited by the Rosetta spacecraft. The volume of a sphere is 4/3 PR cubed, where r is the radius. With a diameter of 2.8 kilometers, the radius is 1.4 kilometers, or 1.4 times 10 to the 5th centimeters. Plug that in, and you get a volume of about 1.1 times 10 to the 16 cubic centimeters. Multiply by density, and you get a mass of roughly 5.5 times 10 to the 15 grams, or 5.5 trillion kilograms. Now suppose a CME hits this object. The momentum delivered depends on how much of the CME actually intersects the nucleus, versus just passing through the diffuse coma. Let's be conservative and assume that the effective cross-sectional area for momentum transfer is roughly the geometric cross-section of the nucleus, about 6 square kilometers, or 6 times 10 to the 11 square centimeters. A CME with a density of say 10 to the minus 15 grams per cubic centimeter, travelling at 1,000 kilometers per second, sweeps out a certain amount of mass per second across that cross-section. The mass flux is density times velocity times area, which gives about 6 times 10 to the 11 grams per second. If the CME lasts for, say, 1 hour or 3,600 seconds, that's a total mass of about 2 times 10 to the 15 grams hitting the nucleus. First possibility, maybe the nucleus is much more massive than we estimated. If the density is higher, say 2 or 3 grams per cubic centimetre, like solid rock instead of fluffy ice, then the mass goes up by a factor of 4 to 6. That would reduce the expected velocity change proportionally, bringing it down to maybe 10 meters per second or less. That's still detectable over time, but it's getting closer to the noise floor of chronograph astrometry. If the nucleus is even denser, maybe it's a fragment of some ancient protoplanetary core with metallic content, then the mass could be higher still. But here's the problem. If the nucleus is that dense, why is it producing such an active coma? Dense objects typically have lower volatile content and produce less outgassing. Yet we see a clear coma and tail in the Hubble images, and spectroscopy shows active CO2 emission. Second possibility, maybe the CME is mostly mist. The nucleus is tiny, only a few kilometers across. The coma is much larger, extending tens of thousands of kilometers, but the coma is mostly empty space with very low density gas and dust. If the bulk of the CME's momentum was carried in a concentrated stream that happened to pass to one side of the nucleus, most of the momentum would blow through the coma without hitting anything solid. The coma might light up, the plasma tail might brighten and compress, but the nucleus itself wouldn't feel much push. This is actually quite plausible. CMEs aren't uniform density clouds, they have structure, with denser filaments and voids. If 3I Atlas got lucky and the dense parts missed it, the deflection could be negligible. Third possibility, maybe the geometry was such that multiple impacts cancelled out. If 3 CMEs hit from slightly different directions, their momentum vectors might partially cancel. This seems unlikely given that all 3 allegedly came from similar source regions on the far side of the Sun, but it's not impossible. CMEs expand and propagate in 3 dimensions, and the exact arrival direction at the object's location might vary depending on the CME's internal structure and how it interacts with the ambient solar wind. But here's where things get interesting. None of these conventional explanations really satisfies me, because they all require fortunate coincidences or fine-tuning. The object would have to be denser than it appears, and more massive than Hubble's size estimate suggests, or the CMEs would have to miss by just the right amount, or the impacts would have to cancel in a very specific way. Any one of these could be true, but when you stack multiple unlikely coincidences together, you start wondering if maybe there's a simpler explanation that involves something we don't understand rather than a conspiracy of lucky accidents. So let's revisit the exotic hypothesis: electromagnetic shielding, or momentum redistribution. Suppose the coma of 3I Atlas has properties that allow it to interact with the CME's magnetic field in a way that redirects or absorbs the momentum without transferring it to the nucleus. How might that work? One mechanism is magnetic pressure. The CME carries frozen-in magnetic field lines. If the coma also has an internal magnetic structure, perhaps generated by currents flowing through ionized gas in the coma, then the 2 magnetic fields can push against each other. The force is distributed over the volume of the coma rather than concentrated on the nucleus. If the coma's magnetic field is strong enough and structured appropriately, it could act like a magnetic cushion, spreading the CME's impact over a large area and converting the kinetic energy into heating and plasma compression rather than bulk motion of the nucleus. Another mechanism is current flow. If the interaction between the coma and the CME induces strong electric currents in the coma, those currents interact with magnetic fields via the Lorentz force. The Lorentz force can act in any direction depending on the geometry of the current and field. If the induced currents are distributed symmetrically in the coma, they could generate forces that partially or fully cancel the direct momentum transfer from the CME impact. This would require a very specific geometry and current distribution, but it's not forbidden by physics. A third mechanism, more speculative still, is that the object itself has a conductive core or internal structure that generates its own magnetic field through dynamo action or frozen-in remnant magnetization. If the nucleus is partially metallic or contains conductive minerals, and if it's rotating or has convective currents in a liquid interior, it could generate a magnetic field like Earth does, only much weaker. That internal field could interact with external plasma in ways that provide magnetic shielding. This sounds far-fetched for a comet, but remember, we're talking about an interstellar object that might be billions of years old, possibly a fragment from a disrupted exoplanet or an object with a formation history completely unlike our solar system's comets. But here's what I find compelling. The mere fact that we're having this discussion means 3I Atlas is pushing the boundaries of our understanding, even if the exotic hypotheses turn out to be wrong. The exercise of working through them teaches us something about the limits of our models and the kinds of observations we'd need to resolve these questions for future interstellar visitors. And if any of the exotic hypotheses turns out to be even partially correct, then we've just discovered a new phenomenon, a new way that small bodies can interact with stellar environments, and that would be genuinely revolutionary for astrophysics. So what does it mean that 3I Atlas didn't budge? It means either we're missing something in our observations, or we're missing something in our models, or we're missing something in our understanding of what kinds of objects can exist in the universe. And any of those possibilities is worth investigating further, because that's how science advances, by confronting observations that don't quite fit and refusing to look away until we understand why. Part 6. Lessons from the first visitors. Before we go any further down the rabbit hole with 3I Atlas, we need to put this object in context by comparing it to the only other confirmed interstellar visitors we've detected. Because the truth is, we're still in the very early days of discovering and characterizing objects that come from beyond our solar system, and every single one so far has been weird in its own way. Understanding those weirdnesses might help us figure out whether 3I Atlas is uniquely strange or just the latest in a series of cosmic oddities that are forcing us to expand our taxonomy of what exists out there in the galaxy. Let's start with One-Eye Oumuamua, discovered in October 2017 by the Pan-STARRS telescope in Hawaii. Oumuamua is a Hawaiian word meaning scout or messenger from the distant past, and it was an apt name because this object was like nothing we'd ever seen. When astronomers first spotted it, they thought it might be a comet or asteroid from our own solar system, but the orbit calculation came back showing a hyperbolic trajectory with an eccentricity around 1.2. It had come from interstellar space, passed through the inner solar system at high speed, and was already on its way back out when we discovered it. What made Oumuamua truly bizarre was its lack of visible coma or tail, despite passing quite close to the Sun, combined with an unexpected non-gravitational acceleration as it moved away from perihelion. Non-gravitational acceleration is common in comets because outgassing produces a rocket effect. The gas jetting from the sunward side pushes the nucleus slightly, altering its orbit in predictable ways. But Oumuamua showed this acceleration without any detectable coma. Observations with Spitzer Space Telescope and other instruments failed to find the infrared signature of dust or gas emission you'd expect from active outgassing. So what was causing the acceleration? Various hypotheses were proposed. Maybe it was outgassing something exotic like pure nitrogen ice or molecular hydrogen that wouldn't produce visible dust. Maybe it was unusually elongated, tumbling end over end, which could explain its dramatic brightness variations and possibly its acceleration pattern. Or maybe, and this is the one that got media attention, it was an artificial object, a light sail or probe from another civilization. That last hypothesis was championed by astronomer Avi Loeb and remains controversial, but it sparked important discussions about how we'd recognize technosignatures if we saw them. Then came 2I Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov using a telescope he built himself. Borisov was almost refreshingly normal compared to Oumuamua. It looked like a comet, acted like a comet, had a clear coma and tail, and spectroscopy showed familiar cometary molecules like water and carbon monoxide. Its orbit was hyperbolic with an eccentricity around 3.4, clearly interstellar in origin, but its behaviour was conventional. It outgassed as it approached the Sun, brightened predictably, showed dust emission in the infrared, all the things Oumuamua didn't do. Borisov proved that interstellar comets can be similar to our own solar system's comets, just coming from farther away. Now we have 3I Atlas with its eccentricity of 6.1, its CO2-rich coma, its apparent electromagnetic interaction with the Sun, and its mysterious resistance to deflection by CMEs. How does it compare to the first two? Let's break it down by categories. Velocity and trajectory. All three are on hyperbolic orbits, but 3I Atlas is moving faster at infinity, about 60 km per second compared to Oumuamua's 26 km per second, and Borisov's roughly 32 km per second. That higher velocity suggests it may have originated from a different region of the galaxy. Possibly the galactic thick disk, which is an older stellar population with different kinematics than the thin disk, where most nearby stars, including our Sun, reside. Size and mass. Oumuamua was estimated to be somewhere between 100 and 1,000 metres in size, depending on assumptions about its shape and albedo. Borisov's nucleus was estimated at around 0.5 kilometre to 1 kilometre. 3I Atlas appears larger based on Hubble measurements, maybe 2 to 3 kilometres, which makes it the biggest of the three by nucleus size, though still small by solar system comet standards. Here's another thought. Maybe the key difference is activity level. Borisov was actively outgassing throughout its passage through the inner solar system, producing a thick coma. Oumuamua was inactive, no coma, just a bare surface. 3I Atlas is actively outgassing, producing CO2 and dust, but maybe not as vigorously as Borisov did relative to its size. If the coma density is in some intermediate range, not too thick and not too thin, maybe that's the sweet spot where electromagnetic effects become important. Too little gas, and you don't have enough plasma to interact meaningfully with the solar wind. Too much gas, and the interaction is dominated by collisional drag rather than electromagnetic forces. The Goldilocks zone for plasma interactions might require just the right level of outgassing. Or maybe, and this is the possibility that keeps me up at night, maybe weird is normal for interstellar objects. Maybe objects that have been wandering the galaxy for billions of years, exposed to cosmic rays, occasional stellar encounters, maybe even gravitational interactions with rogue planets or passages through interstellar clouds. Maybe those objects evolve in ways that our solar system's comets and asteroids don't. Maybe they develop properties, structures, compositions that we can't replicate in our solar system because our objects haven't had that kind of history. If that's true, then every interstellar visitor is an opportunity to study processes and materials that don't exist anywhere in our cosmic backyard. 3I Atlas isn't just a comet from another star system, it's a time capsule from an earlier epoch of galactic evolution, a sample of matter that formed under different conditions and has been processed by different environments than anything we can touch with our spacecraft. And if it's interacting with our sun in ways we've never observed before, that's not just a curiosity, it's a window into physics we've never had a chance to study because we've never had the right laboratory specimens. So where does this comparison leave us? It tells us that 3I Atlas is unusual even among interstellar objects, but it also tells us that unusual might be the norm for this population. It suggests that the short-circuiting hypothesis, while exotic, isn't completely out of left field when you consider that we've already seen one interstellar object with unexplained acceleration, and now we might be seeing another with unexplained electromagnetic behaviour. And it raises the stakes for future observations, because if the pattern holds, if interstellar object number 4 turns out to be weird in yet another way, then we'll have to seriously consider that our entire framework for understanding small bodies in space is incomplete, built on the parochial sample of solar system objects and not generalizable to the wider galactic population. Part 7. The Hidden Data Problem. Let's talk about what we don't know, because in science, acknowledging the gaps in your data is often more important than celebrating what you think you've figured out. And when it comes to 3I Atlas and this entire story about CME impacts and electromagnetic interactions, there are some significant gaps, some tantalizing hints of information that might exist but isn't publicly available, and some questions about whether we're working with the complete picture or just the fragments that have made it into the public domain. Start with what we do have. The discovery announcement came quickly after Atlas detected the object on July 1st, 2025. That's standard procedure for potentially interesting objects. You report them to the Minor Planet Center, other observatories confirm the observations, and the orbit gets refined. Hubble observations on July 21st provided detailed imaging and size constraints. That data was released through NASA's Science Assets Division and reported in various astronomy communications. The James Webb spectroscopy showing CO2-rich coma composition came out shortly after, published through NASA Goddard Space Flight Center. Then there were spectroscopic observations reported in Astronomy and Astrophysics Journal by teams using the Gran Telescopio Canarias, showing interesting polarization properties and potentially unusual dust characteristics. All of that is public, peer-reviewed, or at least officially released through established channels. You can look up the papers, examine the data, verify the claims. That's how science should work. Transparency, replicability, public scrutiny. But here's where it gets murky. The claims about CMEs hitting 3I Atlas and the object not budging are not, as far as I can tell, in any peer-reviewed publication yet. They're emerging from analysis of coronagraph imagery, possibly by independent researchers or amateur astronomers who have access to publicly available data from solar observatories, but aren't part of official mission teams. Now that doesn't automatically make the claims false. Amateur astronomers have made legitimate discoveries before. Gennady Borisov discovered 2I Borisov with a homemade telescope. Crowdsourced data analysis projects have found exoplanets in Kepler data that automated algorithms missed. The democratization of astronomy through publicly available data archives is one of the great success stories of modern science, but it does mean we need to be cautious about accepting claims that haven't been vetted through peer review, especially when those claims are extraordinary. So what data might exist that we don't have access to? First, high-cadence coronagraph observations. Instruments like the GOES-19 coronagraph and SOHO's LASCO coronagraphs take images continuously, but not all of those images are processed and archived publicly in real time. There's often a delay while data is calibrated, while algorithms flag interesting events, while mission teams decide what's worth highlighting. If 3i Atlas appeared faintly in coronagraph frames during late October 2025, those frames exist somewhere, but they might not have been processed with enough care to extract precise astrometry. Coronagraph images are optimized for detecting CMEs and monitoring the solar corona, not for tracking faint comets. Extracting a cometary position from those images requires careful background subtraction, dealing with stray light artifacts, and accounting for the point spread function of the instrument. That's specialized work, and it might not have been done yet by official teams. Second, in situ plasma measurements. This is a big one. Various spacecraft in the inner solar system carry instruments that measure the local plasma environment. Particle density, velocity, temperature, magnetic field strength and direction. Earth-orbiting satellites have these instruments. Mars orbiters have them. The Parker Solar Probe, which is making increasingly close passes to the Sun, has a full suite of plasma instruments. If any of these spacecraft happened to be positioned where they could sample the plasma downstream of 3i Atlas, or even detect remote effects of the object's interaction with the solar wind, that data would be incredibly valuable. But spacecraft data often has an embargo period. Mission teams get exclusive access for months or even years, while they analyse and prepare publications. That data might exist, it might show something interesting, but we won't know until it's released. Third, far-side solar observations. We don't have a spacecraft positioned on the far side of the Sun providing real-time coronal imaging, but we do have helioseismology techniques that can infer active regions on the far side by detecting sound waves travelling through the Sun's interior. We also have the stereo spacecraft, though their positions vary over time, and they can sometimes provide oblique views of the far side. If there were major active regions on the far side in late October 2025, regions capable of producing multiple large CMEs, there should be some evidence of that in the data. But again, has anyone looked specifically for this? Has anyone correlated far side active region emergence with the dates and geometry needed to target 3i Atlas? That kind of detective work requires time and resources, and if nobody's funding it, it won't get done. Let me be clear about something. I'm not suggesting there's a conspiracy or cover-up. I don't think anyone is hiding evidence of alien technology or revolutionary physics. What I am suggesting is that the scientific process is messy and slow, that data doesn't flow from instruments to public archives instantaneously, and that there are legitimate reasons why we might not have the full picture yet. But that also means we need to be humble about our certainty. When someone says 3i Atlas didn't budge when CMEs hit it, we should ask, how do they know? What's the measurement precision? What are the error bars? Has this been independently verified? Has it been peer-reviewed? And when someone proposes an exotic hypothesis like electromagnetic short-circuiting of the Sun, we should ask, what specific predictions does that hypothesis make? What observations would confirm or falsify it? How can we test it with future data? Because that's how science makes progress, not by accepting dramatic claims at face value, but by subjecting them to rigorous scrutiny and demanding evidence. So here's what I think the current state of play is. We have solid evidence that 3i Atlas exists, that it's on a hyperbolic interstellar trajectory, that it has an active CO2-rich coma, and that it passed near perihelion in late October 2025. We have reports, not yet peer-reviewed, that it was detected in coronagraph imagery during superior conjunction and appeared to follow its predicted trajectory. We have claims, even less verified, that multiple CMEs were directed toward it during that period, and we have a hypothesis, highly speculative, that electromagnetic interactions might explain the lack of deflection if deflection should have occurred. Each step in that chain has increasing uncertainty. The further you go from established facts towards speculative interpretation, the more cautious you need to be. But here's why I think this story is worth paying attention to despite those uncertainties. Even if the exotic hypothesis turns out to be completely wrong, the exercise of working through it reveals gaps in our data and understanding that we should fill. It highlights the need for better real-time monitoring of objects passing through the inner solar system. It shows the value of coordinating observations across multiple platforms and wavelengths. It demonstrates that interstellar objects might behave in ways we don't expect, and we need to be prepared to adapt our models when observations challenge our assumptions. And if there is hidden data that eventually gets released, if mission teams or researchers publish analyses that shed new light on 3I Atlas's behaviour during perihelion, then we'll have learned something valuable. Maybe we'll learn that the coronagraph detections were less precise than claimed and the object could have been deflected. Or maybe we'll learn that the detections were solid and there really is a puzzle to explain. Either way, science advances. The transparency question matters beyond just this one object. As we detect more interstellar visitors, and we will, the rate should increase as survey telescopes improve. We need robust systems for sharing data quickly and openly. We need to encourage amateur and professional collaboration. We need to make sure that extraordinary claims are met with extraordinary evidence, but also that we don't dismiss anomalies just because they're inconvenient or don't fit our current models. The history of science is full of examples where weird observations that didn't make sense, at first, turned out to be signposts pointing toward new physics. We just have to be careful to distinguish genuine anomalies from measurement errors or misinterpretations. So the hidden data problem is both a challenge and an opportunity. It's a challenge because it means we can't definitively answer some of the most interesting questions about 3I Atlas right now, but it's an opportunity because as more data becomes available, as more researchers dig into this story, as observational campaigns track the object post-perihelion, we'll gradually build a more complete picture. And that picture might surprise us. It might confirm conventional explanations, or it might reveal something genuinely new about how interstellar objects interact with stellar environments. The only way to find out is to keep watching, keep measuring, keep questioning, and keep demanding transparency in how data is collected, analysed, and shared. Part 8. What if it's not a comet? We've been operating under the assumption that 3I Atlas is essentially a comet, an icy body with volatiles that sublimate when heated by the sun, producing the coma and tail we observe. And maybe that's correct. Maybe it is just a comet, albeit one with unusual composition and possibly unusual behaviour. But let's take a step back and ask a more fundamental question. What if our classification is wrong? What if 3I Atlas is something else entirely? Something that happens to look like a comet in some ways, but has a fundamentally different structure or origin? This is where we need to expand our taxonomy of possible object types. When we think about small bodies in space, we usually categorize them as asteroids, comets, or various subcategories like Kuiper belt objects or centaurs. But that classification scheme is built on decades of observing objects in our solar system. Objects that formed in the same protoplanetary disk around the same star and have similar chemical compositions within certain ranges. Interstellar objects don't have to follow those rules. They could come from systems with different elemental abundances, different formation temperatures, different dynamical histories. They could represent object types that simply don't exist in our solar system, or are so rare here that we've never studied them. Let me walk you through some possibilities that are exotic but not impossible. First, what if 3I Atlas is a fragment of a disrupted exoplanet? Imagine a rocky world, maybe something like Earth or a super-Earth, orbiting another star billions of years ago. Something catastrophic happens. Maybe the planet's star goes supernova. Maybe there's a collision with another planet during a period of late heavy bombardment. Maybe gravitational perturbations from a passing rogue planet tear it apart. The fragments get ejected from the system at high velocity. Most fall back or end up in chaotic orbits, but a few escape into interstellar space. Now, a fragment of a planetary core would have very different properties than a typical comet. It might be much denser, with rock and metal dominating the composition instead of ice. But if that core fragment also had volatiles trapped in its interior, maybe from the original planet's mantle, those volatiles could be released when the object heats up during perihelion passage. You'd see outgassing and a coma, mimicking cometary behaviour, but the nucleus itself would be far more massive and dense than a normal comet. That higher density would make it much more resistant to deflection by CME impacts. The momentum transfer calculations we did earlier assumed cometary density of around 0.5 gram per cubic centimetre. If the actual density is 3 or 5 or even 8 grams per cubic centimetre, like solid rock or iron, the expected deflection drops proportionally. This scenario could also explain the CO2-rich composition. Carbon dioxide can be trapped in minerals as carbonates, like calcium carbonate or magnesium carbonate. If 3I Atlas is a rocky fragment with carbonate minerals, heating during perihelion could decompose those carbonates, releasing CO2. The lack of water would make sense if the fragment came from a dry inner region of its parent planet, or if water was lost during the disruptive event. Second possibility, what if it's an ancient object from the very early galaxy, formed when metallicity was much lower than today? In the early universe, the first generation of stars, population 3 stars, contained only hydrogen and helium, because no heavier elements had been synthesized yet. Those stars exploded as supernovae, scattering the first heavy elements into space. Second-generation stars, population 2, formed from that enriched material, but still had much lower metallicity than modern stars like our Sun. Objects that formed in systems around population 2 stars would have different elemental ratios than what we're used to. Could such an ancient object have survived billions of years wandering the galaxy? It's possible. Space is cold and empty. An object in interstellar space is exposed to cosmic rays which gradually alter its surface chemistry, but the interior can remain pristine. If 3I Atlas is 4 or 5 billion years old, or even older, it could be carrying chemical signatures from a completely different epoch of galactic evolution. Maybe that ancient chemistry includes unusual minerals or compounds that give it electromagnetic properties we don't see in younger objects. Third possibility, and this one is going to sound wild, so buckle up. What if 3I Atlas has a conductive core that acts like a natural electromagnet? Certain meteorites found on Earth, particularly iron meteorites, contain metallic iron-nickel alloys that can hold remnant magnetization. If an object formed in a strong magnetic field environment, like the disk around a highly magnetized young star or near a magnetar, it could acquire a frozen-in magnetic field that persists for billions of years. Now, if 3I Atlas has a metallic core with remnant magnetization, that core would generate a magnetic field extending into the coma. That field could interact with the Sun's magnetic field and the CME's magnetic structure in complex ways, potentially providing the kind of electromagnetic shielding or force redirection that would prevent orbital deflection. Is there any evidence for this? Not directly. We haven't measured 3I Atlas's magnetic field because we haven't sent a spacecraft close enough to do that, but there are some tantalizing indirect hints. Remember the polarization measurements published in Astronomy and Astrophysics? The paper noted a deep negative polarization branch in 3I Atlas's light, meaning that at certain scattering angles, the reflected light shows unusual polarization properties. This can indicate something about the dust grain properties in the coma, their size distribution, shape, and composition. If the dust grains contain metallic inclusions or have unusual shapes, that could affect polarization. And if there are metallic grains in the coma, maybe there's a metallic core in the nucleus. Fourth possibility, what if it's not a single object but an aggregate, a rubble pile held together by weak gravity? Many asteroids in our solar system are thought to be rubble piles, collections of smaller fragments from ancient collisions that never fully recoalesced into a solid body. If 3I Atlas is a rubble pile with a lot of void space between the fragments, its bulk density could be very low even if the individual fragments are made of denser material. But here's where it gets interesting. The voids could be filled with ice or volatiles, and the structure could be layered, with a more porous outer shell and a denser core. When CMEs impact such an object, the forces might be absorbed by the outer layers compressing or shedding material, protecting the core and preventing net momentum transfer. Fifth possibility, and I'm going to say this even though I know how it sounds, what if it's artificial? What if 3I Atlas is not a natural object at all, but a probe or artifact constructed by some other civilization billions of years ago and sent wandering through the galaxy? This is the hypothesis that got so much attention with Oumuamua, and while I personally think it's extremely unlikely, I can't completely dismiss it without evidence. If it were artificial, if it had some kind of propulsion or magnetic shielding technology, that could explain both the lack of deflection and the electromagnetic interactions with the Sun. An advanced civilization might design an interstellar probe to withstand close stellar encounters, to use stars for gravitational assists, or even to harvest energy from stellar magnetic fields. From a distance, such a probe might look like a comet if it was venting gas for cooling or propulsion. But here's the thing. All of these exotic possibilities, from planetary fragments to ancient low metallicity objects, to rubble piles to artificial probes, they all make different predictions. A dense rocky fragment should have a high mass for its size and might show different spectral signatures than an icy comet. An ancient object might have unusual elemental ratios detectable with high-resolution spectroscopy. A magnetized core should create detectable effects on charged particles in the coma. A rubble pile might show different thermal properties or rotational behavior. An artificial object might do things that violate our understanding of physics or show clear signs of technology. So the way forward is obvious. Gather more data, high-resolution imaging to look for surface features, detailed spectroscopy to measure elemental abundances and look for unusual molecules or minerals, polarimetry and radar observations to constrain density and internal structure, radio telescope monitoring to search for any electromagnetic emissions, and if any of these observations reveal something genuinely anomalous, something that can't be explained by natural processes, then and only then should we start taking the more exotic hypotheses seriously. Until then, the most reasonable approach is to assume 3I Atlas is a natural object, probably a comet or comet-like body, but with properties that challenge our current understanding. Maybe it's denser than typical comets. Maybe its coma has unusual electromagnetic characteristics. Maybe it represents a class of interstellar objects we haven't studied before. Those would all be fascinating discoveries that would advance planetary science and astrophysics. We don't need it to be artificial or magical for it to be scientifically important. Weird natural phenomena are exciting enough on their own. So is 3I Atlas a comet, an asteroid, a planetary fragment, an ancient relic, a rubble pile, or something else entirely? Honestly, we don't know yet. And admitting that uncertainty is not a weakness, it's intellectual honesty. The data we have is consistent with several possibilities. The way to narrow it down is to collect more data, test predictions, rule out alternatives systematically. That's the scientific method, messy and slow, but ultimately reliable. And whatever 3I Atlas turns out to be, I guarantee it will teach us something we didn't know before about the diversity of objects wandering through our galaxy. Part 9. The Space Weather Connection. Now we're going to venture into territory that's even more speculative and controversial than anything we've discussed so far, because the claims about 3I Atlas don't stop with electromagnetic interactions and lack of deflection. Some people are suggesting there's a broader connection between this object's solar activity and even conditions here on Earth. Specifically, they're claiming that the same active regions that launched CMEs toward 3I Atlas are rotating into Earth-facing positions, potentially coinciding with a supermoon or full moon alignment, and that this combination could trigger enhanced geomagnetic activity or even seismic events. Let me be absolutely clear before we dive in. This chain of causation, from interstellar object to solar eruption to Earth-directed space weather to earthquakes, is extremely speculative and not supported by mainstream scientific consensus. But it's being discussed, and I think it's worth examining both what tiny grain of scientific plausibility might exist and where the reasoning goes off the rails. Because understanding why certain ideas are appealing even when they're probably wrong is itself a valuable exercise in critical thinking. Let's start with the sun's rotation. The sun rotates on its axis, but it doesn't rotate uniformly, because it's not a solid body, it's a ball of plasma. The equatorial regions rotate faster, completing one rotation in about 25 days, while the polar regions rotate more slowly, taking about 35 days. As seen from Earth, which is also orbiting the Sun, the apparent rotation period is about 27 days. This means that active regions, sunspots, and coronal structures that are visible on one side of the Sun will rotate out of view over the course of about 2 weeks, then reappear on the opposite side 2 weeks later if they persist that long. So if there were major active regions on the far side of the Sun in late October 2025, active enough to produce multiple large CMEs, those regions should have rotated into Earth-facing view sometime in mid-November. Did they? This is something we can check. Solar observatories continuously monitor the Earth-facing hemisphere, cataloguing sunspots and active regions, tracking their magnetic complexity, and forecasting flare and CME probabilities. If major active regions appeared in mid-November that could plausibly be the same ones from late October, that would support at least that part of the story. Could Earth tides trigger earthquakes? There's actually some evidence for this, but it's very subtle. Studies have found weak statistical correlations between tidal stress and the timing of earthquakes, particularly for thrust faults in subduction zones. The correlations are strongest for the largest earthquakes. The idea is that tidal stress doesn't cause earthquakes. But in regions where a fault is already close to failure, the small additional stress from tides could advance the timing by hours or days. It's not that the tide creates the earthquake, it's more like the earthquake was going to happen anyway, and the tide determines exactly when. So now we have 3 separate pieces, all with varying degrees of scientific support. 1. Active regions on the Sun rotating into Earth view, producing CMEs. That happens regularly, it's well documented, nothing controversial. 2. CMEs causing geomagnetic storms, also well documented and routine. 3. Geomagnetic storms somehow triggering earthquakes. Not supported by mainstream science, correlations are weak at best, no plausible mechanism. And 4. Lunar tides modulating earthquake timing. Very weakly supported for specific conditions, but the effect is tiny. The claim then is that all of these factors converging at once, CMEs from active regions that interacted with 3i Atlas, hitting Earth during a supermoon, could create a perfect storm of conditions that increase earthquake risk. And I have to be honest, when you stack that many weak correlations and speculative mechanisms on top of each other, the compound probability of the whole chain being real and significant becomes vanishingly small. But here's why I think this narrative is appealing to some people despite the scientific problems. It creates a storyline, a causal chain connecting cosmic events to terrestrial consequences. It gives human significance to an interstellar visitor, making it not just a scientific curiosity, but something that could affect our lives. It taps into ancient intuitions about celestial omens and cosmic influences, and in a world full of uncertainty and uncontrollable events, it offers the psychological comfort of explanation, even if that explanation isn't actually supported by evidence. This is where scientific literacy becomes crucial, being able to evaluate chains of reasoning, to ask for evidence at each step, to distinguish between established facts and speculative hypotheses, to understand the difference between correlation and causation. These are essential skills. When someone says 3i Atlas is triggering solar eruptions that will cause earthquakes during the full moon, you need to be able to unpack that claim, examine each link, assess the evidence, and recognize where speculation is being presented as fact. That doesn't mean we should completely dismiss space weather as unimportant. Geomagnetic storms are real hazards, particularly for technological infrastructure. A strong enough geomagnetic storm like the Carrington event of 1859 could cause billions of dollars in damage to power grids and satellites today. Monitoring solar activity and forecasting space weather is important work with practical benefits. And if studying interstellar objects like 3i Atlas teaches us something new about how the Sun behaves, how CMEs are triggered, how magnetic structures in the corona evolve, that knowledge could improve space weather forecasting and help protect our technology. But conflating legitimate space weather science with speculative earthquake triggering doesn't help anyone. It muddies the waters, makes it harder for people to distinguish real risks from imagined ones, and undermines public trust in science when the speculative predictions don't pan out. So my position is this. Yes, let's monitor solar activity associated with 3i Atlas. Yes, let's track geomagnetic storm forecasts. Yes, let's study whether there are any unusual patterns emerging. But let's be very careful about drawing causal connections without solid evidence, and let's be honest about what we know versus what we're speculating about. If a major earthquake happens to occur during a period when there's enhanced solar activity and a full moon, is that evidence of causation? No, it's just coincidence unless you can demonstrate a plausible mechanism and show statistical significance above random chance. Large earthquakes happen somewhere in the world every few weeks. Full moons happen every month. Solar active periods happen regularly during the solar cycle. You're bound to get overlaps just by chance. What would convince me there's a real connection? A clear physical mechanism, theoretical modelling showing how geomagnetic fields could plausibly impart enough stress to trigger faults, and multiple independent statistical studies showing consistent correlations that can't be explained by chance or data mining. Until we have that, the space-weather earthquake connection remains in the category of interesting ideas that probably aren't true, but could be worth investigating further just to be sure. As for 3i Atlas's role in all this, the idea that an interstellar comet a few kilometers across could trigger solar eruptions that affect Earth is, to put it mildly, a stretch. The energy scales don't match. The Sun is vastly more powerful than any small body passing through its vicinity. If 3i Atlas is electromagnetically interacting with the Sun at all, which itself is speculative, those interactions would be local and small scale, not enough to fundamentally alter large-scale solar activity patterns that would affect Earth. So while the narrative is dramatic and connects multiple interesting phenomena, the science supporting it is thin to non-existent. But here's what I do find valuable in this discussion. It highlights how interconnected things are. The Sun affects Earth through radiation and plasma. The Moon affects Earth through gravity. Interstellar objects carry information about other star systems and galactic evolution. Space weather impacts our technology and possibly subtle geophysical processes. We live in a dynamic, coupled system where influences propagate in complex ways. Understanding those connections, separating real influences from spurious correlations, that's the work of science. And sometimes, the most valuable thing a wild hypothesis can do is motivate us to collect the data needed to definitively test it, even if the answer turns out to be negative. Part 10. What happens next? We've covered a lot of ground, from orbital mechanics to plasma physics to speculative hypotheses about electromagnetic interactions and space weather. Now let's bring this back to practicalities. What actually happens next with 3i Atlas? What can we observe, and what should we be watching for if we want to see whether any of these wild ideas have merit? First, let's establish where the object is now and where it's going. 3i Atlas reached perihelion, its closest approach to the Sun, on approximately October 29th, 2025. That date might be slightly uncertain depending on which ephemeris you're using, and how non-gravitational forces from outgassing are modelled, but late October is the right time frame. After perihelion, the object is now moving outbound, travelling away from the Sun along its hyperbolic trajectory. It's already passed Earth's orbit again, heading out toward Jupiter's orbit and beyond, gradually fading as it gets farther away and the solar heating that drives outgassing decreases. This means our observational window is closing. The object is getting fainter every day. The coma that made it easier to detect is probably shrinking as sublimation rates drop. Ground-based telescopes and space telescopes can still track it for now, but within weeks or months it will become too faint for all but the largest telescopes to observe. By this time next year, it will likely be beyond practical observational reach, just another faint dot among billions of stars, indistinguishable and lost. This is the nature of interstellar objects. We get one brief chance to study them as they pass through our neighbourhood, and then they're gone forever. So if we want to learn more about 3i Atlas, we need to act fast. What observations should be prioritised? High-resolution imaging to get better constraints on the nucleus size and look for any surface features or shape irregularities. The best ground-based telescopes and Hubble can provide this, though the object's increasing distance makes it harder each day. Continued spectroscopy to monitor how the coma composition changes as the object moves away from the Sun and different volatiles freeze out at different temperatures. This could reveal layering in the nucleus composition or tell us about the thermal properties of the material. Polarimetry observations to follow up on those unusual polarization results and see if the properties change with distance or phase angle. Radio observations would be fascinating. You could search for any natural radio emissions from the coma, though these are typically very weak for comets. You could also attempt radar observations, bounce a radio signal off the nucleus and measure the return, which gives you information about size, shape, rotation rate, and surface properties. Radar observations require the object to be relatively close, and the telescope to be very sensitive, so the window for this is probably already closed, but it's worth checking. One critical observation would be precise astrometry over the coming weeks. If there was any deflection from CME impacts, continued tracking should reveal it as the object's position progressively deviates from the pre-perihelion ephemeris. The deflection would compound over time, making it easier to detect after perihelion than during the coronagraph observations when uncertainties were large. If independent observers using ground-based telescopes now that the object is out of the Sun's glare find that 3i Atlas is exactly where the original orbit predicted, that strengthens the case that no significant deflection occurred. If they find a deviation, that's extremely interesting and demands explanation. There's also the question of what the Sun does next. If active regions from late October have rotated into Earth-facing view and are still active, we should see them in current solar imagery. Sunspot groups are tracked and numbered by solar observatories, so we can check whether any major groups appeared in mid-November that could plausibly be the ones from the far side in late October. If those regions produce more CMEs, we can observe them directly with coronagraphs and spacecraft instruments. If there's any repeat of unusual behaviour, any correlation with 3i Atlas's position, even though the object is now on the opposite side of the Sun from Earth's perspective, that would be worth noting. Then there's the broader monitoring question, space weather forecasting. NOAA's Space Weather Prediction Centre and similar agencies around the world continuously monitor solar activity and issue forecasts for geomagnetic storm probabilities. If there is enhanced solar activity associated with those active regions, if CMEs are launched toward Earth, if geomagnetic storms occur, all of that will be documented and publicly reported. We can compare the timing to lunar phases and to any seismic activity. I expect we'll find what we always find. Solar activity follows the solar cycle with some random variability. Geomagnetic storms happen when CMEs hit Earth, regardless of lunar phase or interstellar objects, and earthquakes happen according to tectonic processes with no meaningful correlation to space weather. But documenting this is still valuable because it's how we test and potentially refute speculative hypotheses. Looking further ahead, what happens when we detect interstellar object number 4? We will detect more, that's essentially certain. Improved survey telescopes like the Vera Rubin Observatory, which is scheduled to begin operations soon, will dramatically increase our ability to detect faint moving objects. We should be discovering multiple interstellar visitors per year once these surveys reach full capacity. Each new detection is an opportunity to test our understanding. If the next interstellar object shows electromagnetic anomalies or unexpected deflections, that would suggest 3i Atlas wasn't unique, and there might be a real phenomenon to study. If the next several interstellar objects behave conventionally, that would suggest 3i Atlas was either misinterpreted or represented a rare edge case. There's also the possibility, however remote, of a dedicated mission to an interstellar object. The proposals for rapid response missions to intercept interstellar visitors have been discussed for years. The technical challenges are immense. You need to detect the object early enough to plan and launch a mission, you need a spacecraft that can reach the high velocities required for interception, and you need to do all of this on a tight timeline because the object is passing through quickly. But it's not impossible. If an interstellar object were discovered while still beyond Jupiter's orbit, and if there was sufficient political will and funding, a mission could potentially be mounted. Such a mission could carry instruments to measure magnetic fields, plasma properties, composition, internal structure, all the things we can't reliably determine from Earth-based observations. That would definitively answer many of the questions we're grappling with now. In the absence of a dedicated mission, our best hope for in situ data is serendipitous encounters. Spacecraft already in the inner solar system, like the Parker Solar Probe or Solar Orbiter, or even Mars orbiters, might pass near enough to an interstellar object's trajectory or tail to sample the plasma environment downstream. If any spacecraft happened to cross through 3i Atlas's plasma tail during the perihelion passage, their instruments might have recorded useful data. This kind of fortuitous observation has happened before with comets, and it's worth checking mission data archives to see if any spacecraft were positioned favourably. There's also the citizen science angle. Amateur astronomers and independent researchers can contribute meaningfully to tracking interstellar objects. They can report observations, contribute to light curve monitoring, analyse publicly available data from space telescopes and solar observatories. The chronograph detections that started this whole story may have come from exactly this kind of independent analysis. As data becomes more accessible and processing tools become more powerful, the line between professional and amateur astronomy blurs. That's a good thing for science, as long as claims are properly vetted and extraordinary assertions are backed by extraordinary evidence. So what should you personally be watching for if you want to follow this story? First, keep an eye on astronomical telegram circulars and preprint servers for any papers about 3i Atlas. particularly anything addressing the perihelion observations, trajectory analysis, or compositional studies. Second, monitor space weather reports for any unusual solar activity from mid-November onward that might be related to the active regions in question. Third, if you have access to a telescope or know someone who does, tracking 3i Atlas over the coming weeks and comparing observed positions to predicted ephemeris is valuable data. Fourth, stay skeptical but open-minded. Extraordinary claims require extraordinary evidence, but science advances by taking anomalies seriously and investigating them rigorously. What are the stakes here? If 3i Atlas turns out to be a conventional comet that behaved exactly as expected, we've still learned something about interstellar object diversity and gotten practice studying these rare visitors. If it turns out there were measurable but small deflections from CME impacts, we learn about momentum transfer in rarefied plasma environments. If there's evidence of electromagnetic interactions beyond what standard models predict, that opens entirely new avenues for plasma astrophysics research. And if, against all odds, there's something genuinely inexplicable about this object, something that forces us to revise fundamental theories, that would be the kind of paradigm-shifting discovery that comes along once in a generation. My prediction? We'll find that most of the mystery evaporates under closer scrutiny. The deflections will turn out to be within measurement uncertainties, or explainable by conventional physics once we have better data. The electromagnetic interactions will be either artifacts of data processing or modest effects consistent with known plasma physics. The space weather connections will turn out to be coincidental timing with no causal relationship, and 3i Atlas will join Oumuamua and Borisov in the category of interstellar visitors that taught us something new about the diversity of objects in the galaxy, but didn't require revolutionary new physics to explain. But I could be wrong. That's what makes this exciting. We don't know yet. The data is incomplete, the analysis is ongoing, and nature has surprised us before. So let's keep watching, keep measuring, keep questioning. Let's demand evidence but remain open to possibilities. Let's separate what we know from what we think we know from what we're speculating about. And let's remember that even if 3i Atlas turns out to be less mysterious than it first appeared, the exercise of investigating it rigorously is never wasted effort. That's how science works. That's how we learn. Part 11. The Chemistry of Distant Worlds. Let's shift gears and talk about something that's been happening simultaneously with the 3i Atlas story, but in a completely different corner of astronomy. Because while we've been tracking this interstellar visitor, the James Webb Space Telescope has been quietly revolutionizing our understanding of exoplanet atmospheres, and one recent discovery connects thematically to what we've been discussing about unusual chemical compositions. In early 2025, JWST observations revealed an exoplanet orbiting a star about 200 light-years away, with an atmosphere that doesn't make sense according to our standard formation models. The planet is roughly Neptune-sized, orbiting in the temperate zone where liquid water could exist on a surface if the planet had one. But the atmospheric spectroscopy shows something unexpected. The atmosphere is dominated by carbon dioxide at levels far higher than models predict, with very little water vapour and unusual ratios of carbon-bearing molecules. This matters because when we build models of how planets form, we use our solar system as the primary template. Planets form in protoplanetary disks from gas and dust. The composition depends on temperature gradients in the disk. Close to the star it's hot and only refractory materials condense. Farther out it's cool enough for water ice to form. Even farther out carbon dioxide and other volatiles freeze. The chemical makeup of a planet should reflect where in the disk it formed and what materials were available there. An atmosphere rich in carbon dioxide but poor in water suggests formation in a region or under conditions very different from what we see in our solar system. Now connect this to 3i Atlas. We have an interstellar object with a coma unusually rich in carbon dioxide, different from typical solar system comets that are dominated by water ice. Both the exoplanet and the interstellar comet are showing us that carbon dioxide can be more important in some cosmic environments than our local experience suggests. This tells us something profound about the diversity of planetary systems and the objects they produce. Maybe systems that form from molecular clouds with different carbon to oxygen ratios produce objects with different volatile inventories. Maybe the temperature history during formation matters more than we thought, with carbon dioxide being preferentially retained in certain thermal regimes. Maybe there are classes of exoplanetary systems we haven't sampled yet that routinely produce carbon dioxide-rich worlds and ejected comets. JWST's ability to do transmission spectroscopy, watching starlight filter through exoplanet atmospheres during transits, and measuring which wavelengths are absorbed by specific molecules, has opened a new era in understanding planetary diversity. We're finding hot Jupiters with clouds made of rock vapour and iron droplets. We're finding temperate worlds with methane signatures that might indicate biological activity, or might just be geological. We're finding planets with atmospheric compositions that don't match anything in our solar system. And here's the connection. If we're seeing this much diversity in bound planets still orbiting their stars, imagine how much diversity exists among the ejected objects wandering between stars. Every planetary system probably produces millions of comets and small bodies during its formation and early dynamical evolution. Some fraction of those get ejected into interstellar space through gravitational interactions. They're carrying chemical signatures from their birth systems, potentially preserving information about stellar abundances and disk chemistry from different places and times in galactic history. 3I Atlas might be a sample of a planetary system that formed from unusually carbon-rich material, or one that experienced different thermal processing during planet formation. Its CO2-rich coma could be telling us about the chemical conditions in a stellar nursery that existed billions of years ago, possibly light years from here. It's a flying archive of extraterrestrial chemistry, and we have this brief opportunity to read what it contains before it vanishes into the darkness between stars. This is why spectroscopy of interstellar objects is so valuable scientifically. Each object is potentially unique, carrying information we can't get any other way. And as JWST continues discovering exoplanets with unexpected atmospheric compositions, we're building a broader context for understanding how diverse planetary chemistry can be. That context helps us interpret interstellar visitors. When we see something unusual in 3I Atlas's spectrum, we can ask, do we know of any exoplanets or stellar environments where such composition might be typical? The future of this field is incredibly exciting. We're going to discover more exoplanets with weird atmospheres. We're going to detect more interstellar objects with unusual compositions, and gradually we'll build up a catalogue of chemical diversity that spans the galaxy. We'll identify patterns, maybe classify objects by their formation environments, or parent star types. We'll learn to read the chemical fingerprints that tell us where an object came from, and what it experienced during its journey through space. And maybe, just maybe, we'll find evidence of truly exotic chemistry, molecules or isotopic ratios that suggest formation under conditions we've never imagined. That's the promise of studying both exoplanets and interstellar visitors. They expand our understanding of what's possible, what nature actually does out there in the universe, beyond the small sample of worlds we can study up close in our own solar system. Part 12, The Sun's Violent Awakening. While we've been focused on 3I Atlas, the Sun itself has been putting on quite a show. Solar Cycle 25, which began around 2019 and is projected to peak around 2025, has been more active than initially predicted, and in mid-2025 we witnessed one of the most powerful solar flares in decades, an X-class flare that erupted from an active region on the Sun's eastern limb and sent a massive coronal mass ejection racing through the inner solar system. This event is worth discussing because it illustrates just how dynamic and unpredictable the Sun can be. Even with our sophisticated monitoring and modelling capabilities, the active region that produced this extreme flare wasn't particularly large or complex when it first rotated into view. Solar forecasters assigned it a moderate probability for producing significant flares, but as it evolved over several days, magnetic flux continued emerging from below the photosphere, building up energy in twisted and sheared magnetic structures in the corona. Then, suddenly, magnetic reconnection triggered, and the stored energy was explosively released. The flare itself produced an intense burst of X-rays, an extreme ultraviolet radiation that caused radio blackouts on the daylight side of Earth. The associated CME, travelling at over 2,000 kilometers per second, reached Earth in less than 24 hours, unusually fast for such eruptions. When it hit our magnetosphere, it triggered one of the strongest geomagnetic storms in recent years, with auroras visible as far south as the Mediterranean and southern United States. Satellite operators reported anomalies, GPS signals showed increased errors, and power grid operators had to take precautionary measures to protect transformers from induced currents. This event reminded everyone that for all our technological advancement, we're still vulnerable to space weather. The sun is not a stable, predictable object. It's a roiling ball of magnetized plasma with internal dynamics we still don't fully understand. Our models of the solar cycle can predict general trends, when activity will be high or low, but they can't tell us when a specific active region will explode or how powerful the eruption will be. Now connect this to the 3i Atlas story. If the sun can produce unexpectedly powerful eruptions from active regions that looked relatively benign, is it really so implausible that far-side active regions could have produced multiple large CMEs in late October? Not really. The sun is capable of producing multiple major eruptions in short succession. We've seen it happen before. The question isn't whether the sun can do it, it's whether those eruptions actually occurred and whether they intersected 3i Atlas's path. The mid-2025 extreme flare also forced solar physicists to revisit their solar cycle 25 predictions. The current cycle has been consistently more active than the initial forecast suggested. Sunspot numbers are higher, flares are more frequent, and the cycle may peak sooner and stronger than predicted. This isn't a failure of the models exactly. It's more that the sun's internal dynamo has variability that's difficult to predict years in advance. We can forecast trends, but individual cycles can surprise us. There's a lesson here about uncertainty and prediction. We often talk about scientific models as if they're crystal balls, telling us exactly what will happen. But models are simplifications of reality, based on incomplete data and imperfect understanding. They give us probabilities and ranges, not certainties. When reality deviates from predictions, that's not necessarily evidence that the models are wrong. It might just mean we're seeing a statistically rare but still possible outcome. This is relevant to how we think about 3i Atlas and any potential electromagnetic interactions. If such interactions exist, they would be operating in a regime where solar physics is already complex and not fully predictable. We can't perfectly forecast when and where CMEs will occur, even without exotic influences from interstellar objects. So if someone claims that 3i Atlas triggered CMEs, we're dealing with a system that already has inherent unpredictability. Distinguishing signal from noise, correlation from causation, becomes extremely difficult. The increasing solar activity also means that space weather hazards are growing as we move towards solar maximum. More CMEs will be launched, more geomagnetic storms will occur, more auroral displays will dazzle observers at high latitudes. This is the natural rhythm of the solar cycle, driven by the 11-year cycle of magnetic field polarity reversal and the winding up of magnetic flux below the photosphere. It has nothing to do with interstellar objects or lunar phases or any external influence. It's the sun doing what the sun does, and we're along for the ride trying to predict and prepare for its outbursts as best we can. As we push further into Solar Cycle 25's peak years, we should expect more extreme events. Power grid operators need to maintain vigilance. Satellite designers need to account for increased radiation exposure. Astronauts on the International Space Station or future lunar missions need radiation protection during solar particle events. These are practical concerns with real consequences. Understanding solar physics isn't just academic curiosity, it's infrastructure protection and human safety. And who knows, maybe the data collected during this active solar period will shed light on exotic phenomena like potential interactions with passing interstellar objects. The more we observe, the more we measure, the better our models become. Even if the 3i Atlas story turns out to be a case of overinterpretation, the observations and discussion surrounding it might motivate new research into solar object interactions that wouldn't have happened otherwise. That's the silver lining of even speculative scientific claims. They can inspire investigations that advance knowledge even when the original claim is refuted. Part 13, When Machines See What We Cannot. Here's something that connects to our 3i Atlas story in an unexpected way: the increasing role of artificial intelligence and machine learning in astronomy. Because whether we're talking about detecting faint comets in coronagraph images, forecasting solar eruptions, or predicting plasma tail behavior, machine learning is becoming an essential tool for handling the massive amounts of data modern telescopes produce. Consider the detection problem. Coronagraph images are complicated. You have the bright corona, CME structures racing outward, cosmic ray hits creating spurious bright pixels, instrumental artifacts from scattered light. Finding a faint comet in that mess is like finding a specific snowflake in a blizzard. Traditional image processing can do it, but it requires careful background subtraction, multiple frames for comparison, and human judgment about what's real versus what's noise. Machine learning offers a different approach. Train a neural network on thousands of coronagraph images containing known comets and other features. Teach it to recognize the patterns that distinguish real objects from artifacts, then let it analyze new images automatically. Several research groups are developing exactly these kinds of tools. Machine learning algorithms that can detect CMEs in solar imagery, classify active regions by their flare potential, identify previously unknown objects in survey telescope data. These algorithms don't replace human astronomers, but they augment human capabilities by rapidly processing vast data sets and flagging interesting features for closer examination. In early 2025, one research team published results from a machine learning model that predicts CME arrival times and speeds based on coronagraph observations of the CME launch combined with solar wind background conditions. The model was trained on decades of historical data from spacecraft like SOHO and Stereo, learning the relationships between observable CME properties and their behavior during propagation through interplanetary space. The result is a forecasting tool that outperforms traditional physics-based models in certain conditions, particularly for complex CMEs with irregular structure. Now imagine applying such a tool to the 3i Atlas situation. You could input the known orbit, the estimated coma properties, the dates and characteristics of the alleged CMEs, and simulate whether those CMEs would have intersected the object and what deflection you'd expect. You could vary the parameters within their uncertainty ranges, exploring a range of scenarios. The machine learning model could identify which combinations of parameters are consistent with the observed lack of deflection and which require fine-tuning or special conditions. This kind of analysis hasn't been done yet for 3i Atlas as far as I know, but it's exactly the type of investigation that would help resolve the questions we've been discussing. Instead of relying on back-of-the-envelope calculations and hand-waving arguments, you'd have quantitative simulations exploring the parameter space systematically. That's how you turn speculation into testable science. There's also machine learning for spectroscopy. Analyzing spectra to identify molecular lines, measure abundances and infer physical conditions is traditionally labor-intensive, requiring expert knowledge of atomic and molecular physics. Neural networks trained on synthetic spectra and laboratory measurements can now do this automatically with accuracy comparable to expert human analysis. For an object like 3i Atlas with its unusual CO2-rich spectrum, machine learning could help identify subtle features or anomalous line ratios that might hint at unusual chemistry or excitation conditions. Another application is in predicting cometary behavior. Comets are notoriously unpredictable because their outgassing depends on complex surface and subsurface processes. Machine learning models trained on observations of many comets can learn patterns in how comets brighten and fade, how their coma structures evolve, how their non-gravitational forces behave. These models can then predict the behavior of newly discovered comets, including interstellar ones, helping observers plan efficient observation campaigns. The exciting thing about machine learning in astronomy is that it can discover patterns humans might miss. Neural networks are good at finding correlations in high-dimensional data where intuition fails. Maybe there are subtle patterns in solar activity that precede CME eruptions, patterns too complex for human forecasters to recognize consciously, but which machine learning can extract from historical data. Maybe there are relationships between comet composition and plasma tail morphology that would help us understand electromagnetic interactions. Machine learning can find these patterns if they exist. But there's a caution here too. Machine learning models are only as good as their training data. If you train a model on solar system comets and then apply it to interstellar objects that might have fundamentally different properties, the model might give misleading predictions. If your training data doesn't include examples of electromagnetically anomalous objects, because such objects are rare or unprecedented, the model won't recognize them when they appear. Machine learning is powerful but not magical. It extends our capabilities, but it doesn't replace the need for careful observation, physical understanding, and critical thinking. Looking forward, as we detect more interstellar objects, and as our solar monitoring capabilities improve, Machine learning will play an increasing role in analysing this data. We'll develop models that can quickly assess whether a newly discovered interstellar object is likely to behave conventionally or show anomalies. We'll have better forecasts of space weather and how it might interact with objects passing through the inner solar system. We'll be able to run thousands of simulations exploring different scenarios, helping us understand which observations would be most valuable for distinguishing between competing hypotheses. The combination of better instruments, more data, and smarter algorithms is accelerating the pace of discovery in astronomy. We're entering an era where survey telescopes will find thousands of asteroids, comets, and potentially interstellar visitors every night. Human astronomers can't possibly examine every detection manually. Machine learning will be essential for triaging the data, identifying the truly interesting objects, and enabling rapid follow-up. In that future, an object like 3I Atlas would be flagged by algorithms within hours of detection, its unusual trajectory recognized immediately, observation campaigns automatically triggered at multiple facilities worldwide. We're not quite there yet, but we're moving in that direction. And when we combine machine intelligence with human curiosity, when algorithms handle the data processing while humans ask the creative questions and interpret the results, that's when breakthroughs happen. That's how we'll solve mysteries like 3I Atlas, by bringing all our tools to bear and refusing to be satisfied with easy answers. Part 14. Cosmic Messengers and Ancient Rocks. Let's talk about something that might seem unrelated at first, but connects thematically to our discussion of interstellar visitors and what they can teach us. Recent findings from asteroid sample return missions that revealed surprising properties about the internal structure and composition of small bodies. In late 2024 and early 2025, scientists analysing samples returned by OSIRIS-REx from asteroid Bennu published startling results. The samples contained a higher proportion of hydrated minerals than expected, evidence of extensive water-rock interactions in Bennu's parent body. But more surprisingly, they found tiny inclusions of highly reflective material, possibly metal-rich grains distributed throughout the matrix. Detailed analysis suggested these inclusions had unusual elemental ratios, enriched in certain heavy elements beyond what typical solar system formation models predict. The interpretation is still being debated, but one possibility is that Bennu's parent body, the larger asteroid from which Bennu is a fragment, incorporated materials from multiple sources during formation. Perhaps it formed at the boundary between different regions of the protoplanetary disk, or perhaps it accreted some material that had been processed through a previous generation of planet formation and disruption. The point is that even asteroids, which we tend to think of as simple, primitive bodies, can have complex histories and heterogeneous compositions. This matters for our 3I Atlas discussion, because it reminds us that small bodies can surprise us. If a solar system asteroid that formed here, from the same nebular material as Earth and the other planets, can have unexpected density variations and unusual mineral inclusions, why shouldn't an interstellar object that formed in a completely different system potentially be even more surprising? The Hayabusa 2 mission samples from asteroid Ryugu told a similar story. Internal heterogeneity, evidence of parent body aqueous alteration, and hints of complex thermal history. These asteroids aren't just piles of uniform rubble, they're geological archives recording billions of years of processing. Now extrapolate to interstellar objects. 3I Atlas has been wandering the galaxy potentially for billions of years, is being exposed to cosmic rays that alter surface chemistry. It may have passed through interstellar clouds where it could accrete new material. It might have had close encounters with other stars that heated it temporarily. All of these processes could modify its structure and composition in ways that solar system objects never experience. So when we try to estimate 3I Atlas's mass and density from limited photometric observations, we're making assumptions based on solar system comets and asteroids. But what if those assumptions are wrong? What if interstellar objects routinely have internal structures that are more heterogeneous, or density profiles that are different, or mineral compositions that reflect their exotic origins and histories? The sample return missions are teaching us that even relatively nearby objects we can study in detail are more complex than we assumed. Interstellar objects are likely to be even more surprising. This connects to another recent finding, analysis of pre-solar grains in meteorites, tiny dust particles that formed around other stars before our solar system existed and got incorporated into primitive meteorites. These grains are identified by their unusual isotopic ratios that don't match solar system material. When analysed with modern techniques, some of these grains show evidence of formation around specific types of stars, red giants or supernovae, based on their elemental and isotopic compositions. The exciting thing is that these presolar grains are microscale samples of interstellar material. They're the closest thing we have to physically touching matter from other star systems. And what they show is that material from different stellar environments has recognisably different properties. Carbon grains from red giant atmospheres have different isotopic signatures than silicon carbide grains from supernovae. This means that if we could analyse a sample from 3I Atlas, we might be able to determine what type of star system it came from, or at least constrain the possibilities based on its isotopic fingerprint. Unfortunately, we can't collect a sample. The object is too far away and moving too fast. But we can do spectroscopy, which gives us some of the same information. High-resolution spectroscopy can measure isotopic ratios for abundant molecules like carbon dioxide. If 3I Atlas has unusual carbon-13 to carbon-12 ratios, or oxygen-18 to oxygen-16 ratios, that would tell us something about its origin environment. Maybe it formed around a star with a different metallicity than our Sun, or one that had incorporated material from a nearby supernova. These kinds of measurements are at the edge of what's currently possible with available telescopes and the faintness of the object. But as observational capabilities improve, as the next generation of extremely large telescopes come online, this kind of detailed isotopic analysis of interstellar visitors will become routine. We'll be able to chemically fingerprint these objects and potentially trace them back to specific regions or populations in the galaxy. The sample return missions are also teaching us about the value of direct physical analysis versus remote sensing. There's information you can only get by holding a sample in your laboratory, measuring its properties with instruments that can never be flown in space. That's why there's such interest in potential sample return missions to interstellar objects. Despite the enormous technical challenges, the scientific payoff would be immense. Imagine if we could intercept an interstellar object and collect even a tiny sample, just a few grams of material, and return it to Earth. We could do isotopic analysis with precision that reveals its stellar origin. We could study organic molecules to search for prebiotic chemistry from another star system. We could measure mineral compositions and crystal structures to understand formation conditions. We could search for amino acids, complex organics, maybe even signatures of life if we got extraordinarily lucky. That's the dream anyway. The reality is that such missions are extraordinarily difficult and expensive, but they're not impossible, and as we detect more interstellar visitors, as we characterize their orbits earlier, we'll eventually have an opportunity where a mission is feasible. When that happens, the sample we retrieve could answer questions we've been asking for generations about the nature of matter beyond our solar system, the diversity of planetary systems, and maybe even the prevalence of the building blocks of life throughout the galaxy. Until then, we rely on remote observations, on spectroscopy and photometry and astrometry, piecing together what we can from photons that travelled across space to reach our detectors. It's detective work with incomplete clues, but it's the best we can do. And sometimes, as with 3I Atlas, the incomplete clues suggest something strange enough to make us question our assumptions and push the boundaries of our understanding. That's progress. Part 15. The Bigger Picture. We've journeyed through orbital mechanics, plasma physics, solar dynamics, space weather, exoplanet chemistry, machine learning, and sample return missions. We've examined claims ranging from solidly established to wildly speculative. Now let's step back and look at the bigger picture, because the story of 3I Atlas, regardless of how it ultimately resolves, is part of something larger happening in astronomy right now. We're living through a revolution in our understanding of the universe, driven by new instruments and new techniques that are revealing phenomena we never knew existed. 20 years ago, we had detected only a handful of exoplanets, and none beyond our solar system. Today we know of thousands of exoplanets with incredible diversity. We've found planets orbiting binary stars, planets around dead stellar remnants, planets in the habitable zones of distant suns. We've characterized exoplanet atmospheres and found molecules that hint at complex chemistry. Similarly, interstellar objects were theoretical until 2017 when we discovered Oumuamua. Now we have 3 confirmed interstellar visitors, and we're developing the observational infrastructure to find many more. Within a decade, studying interstellar objects will transition from rare opportunistic observations to systematic surveys with statistical samples large enough to understand their population properties. Gravitational wave astronomy began in 2015 with the first detection of merging black holes. Today we routinely detect dozens of gravitational wave events per year, opening a completely new window on the universe that reveals phenomena invisible to telescopes. We're finding neutron star mergers, measuring cosmic expansion rates, testing general relativity in extreme gravity regimes. Fast radio bursts, mysterious millisecond duration pulses of radio emission from cosmological distances were first discovered in archived data in 2007 but are now detected daily. We still don't fully understand what produces them, but we're collecting enough data to constrain theories and maybe solve the mystery soon. All of these disparate fields share a common theme. We keep finding things that don't quite fit our existing categories. Objects and events that sit at the boundaries of our theoretical frameworks, challenging us to expand our thinking. Oumuamua doesn't fit neatly into comet or asteroid categories. Some exoplanet atmospheres don't match our formation models. Some gravitational wave sources have unexpected properties. Some fast radio bursts show patterns that hint at complex physics or even, in the wildest speculation, technological origins. This is a pattern throughout the history of science. When we develop new instruments that let us observe previously inaccessible regimes, we almost always find surprises. Radio astronomy revealed quasars and pulsars. X-ray astronomy revealed neutron stars and black holes. Infrared astronomy revealed cool stars and dusty galaxies. Every time we open a new window on the universe, nature shows us something we didn't predict. 3i Atlas fits this pattern perfectly. It's an object we could barely detect a few years ago, observed with instruments that are pushing the limits of what's technically possible, showing behaviour that might or might not challenge our standard models. It represents the frontier, the edge of what we know and understand, the place where science makes progress by confronting anomalies and refusing to look away. Now, most anomalies turn out to have conventional explanations once we understand them better. Pulsars seemed weird at first. People joked about little green men signals, but they turned out to be rotating neutron stars with powerful magnetic fields, exotic but natural. Oumuamua's acceleration probably has a natural explanation involving outgassing or unusual shape, not aliens. And 3i Atlas's resistance to deflection probably has a natural explanation involving measurement uncertainty or conventional physics we haven't properly accounted for yet. But the process of investigating anomalies is never wasted. Even when the answer turns out to be mundane, we learn something. We improve our models, refine our measurement techniques, expand our understanding of what's possible, and occasionally, very occasionally, an anomaly turns out to be genuinely revolutionary. Something that forces us to rewrite textbooks and rethink fundamental assumptions. You never know in advance which anomalies are which. You have to investigate all of them seriously to find the rare ones that matter. So here we are, with an interstellar visitor that might have shown unusual electromagnetic interaction with the Sun, or might just be a normal comet that we're overinterpreting due to limited data. The scientific process will sort it out eventually. More observations will be made, better analyses will be published, alternative explanations will be proposed and tested. The truth will emerge, messy and uncertain at first, then gradually coalescing into consensus as evidence accumulates. What can we take away from all this? First, the universe is full of wonders, more diverse and strange than we imagine even with our best theories. Second, interstellar objects are valuable probes of cosmic diversity, carrying information about distant stellar systems and galactic evolution. Third, space weather is real and important, affecting our technology and potentially teaching us about plasma physics in extreme environments. Fourth, the tools we're developing, from machine learning to sample return missions to next-generation telescopes, are giving us unprecedented ability to study these phenomena. And fifth, maintaining curiosity while exercising skepticism is the right balance for understanding frontier science. Whether 3i Atlas short-circuited the Sun or not, whether it's a dense planetary fragment or a fluffy comet, whether its CO2-rich composition tells us something profound about its birth system or is just a chemical accident, it has already served a valuable purpose. It's made us think, question, calculate, and wonder. It's inspired discussions about plasma physics and orbital mechanics, and electromagnetic interactions that might lead to new insights even if the original hypothesis is wrong. It's reminded us that the cosmos is vast and full of objects wandering through the darkness, occasionally passing close enough for us to glimpse them briefly before they vanish forever. So keep watching the skies, keep supporting astronomical research and space missions, keep asking questions and demanding evidence, keep that sense of wonder alive, that feeling of standing on a tiny planet looking out at a universe that is stranger and more magnificent than we can fully comprehend. Because somewhere out there, right now, another interstellar visitor is on its way. Another cosmic mystery is waiting to be discovered. Another opportunity to learn something new about the universe we inhabit is approaching. And when it arrives, we'll be ready, with our telescopes and our equations and our insatiable curiosity, to decode whatever secrets it carries from the darkness between stars. The story of 3i Atlas isn't over yet, but whether it ends with revolutionary discoveries or conventional explanations, it's been a reminder of why we study the cosmos in the first place, not just to catalogue and classify, but to encounter the unexpected, to be challenged and surprised, and to continually expand the boundaries of human knowledge. That's the promise and the adventure of astronomy, and objects like 3i Atlas are our guides into the unknown.